Well, folks, good morning, good afternoon, good evening, all around the world. We've got many people tuned in once again to the AFuzion monthly technical safety critical training webinar. It's really my pleasure today, this month, to be hosting Perforce. My colleagues and friends, Courtney and Steve, will be giving you a great presentation on artificial intelligence, defense platforms, static analysis, process controls, how to make better systems, how to secure safety of flight in the autonomous world, not just aircraft, systems, ground, space. Anything with a computing device really is a complex system these days. Well, how do we improve determinism? How do we accommodate autonomy, artificial intelligence? What's the role of static analysis? In this quick 45 minutes, and yes, we will be done in 40 to 45 minutes. We're going to cover all these technical topics once again. We've got a lot to cover. When you have a question, you can simply enter it in that question dialog box. Hopefully we'll have an extra 5 or 10 minutes at the end of the presentation to cover those. If we don't, we'll get back to you by email, and you'll see our email addresses, contact information at the last slide here in 45 minutes. So with that, let's begin. Our agenda today is first, real quick, to introduce AFuzion and Perforce. And then we're going to provide an overview of autonomy, AI. What are the characteristics of those systems? Now, in many cases, and increasingly, we need security, certification. Think about your Android, your iPhone. It's not a critical device, right? Well, wait, you're lost. You're stuck in a building. Help, fire. Now, it's safety critical to use. What is the certification implication of that? What are the potential solutions for process controls, static analysis of software? And then we'll end with a question and answer session, our usual monthly format. Now, real quick, most of you know about AFuzion and Perforce. At AFuzion, we've done, this is an old slide, over 500 safety critical, mostly aviation projects, on-site, off-site, 35 countries. We've got 55 senior engineers, and look at me, I'm not real young. We've got decades of experience, each person. We optimize processes for developing systems. We architect software systems, safety analysis. We do certification, mentoring, auditing. Many clients, 15,000 worldwide, engineers, 300 clients, they use our templates checklist. We do mentoring training, and we've trained many, many engineers worldwide. At Perforce, and they'll tell you more in a few minutes, they deliver leading edge products that completely span the entire demands of the whole DevOps lifecycle. They bring really creative, imaginative solutions to life more quickly with improved business changing outcomes. 250 Fortune 500 companies, that's over half of them, rely on Perforce in regulated, safety critical, high stack software environments. There's 1,500 DevOps experts around the world that solve problems, think, across 25 countries. With that, folks, let's begin to think. Traditional safety critical systems, they had very detailed requirements. We had to assess, does implementation meet the requirements to minimize the assumptions made by developers? Remember assumptions? As a pilot, yeah, I am. They're usually wrong. So traditional systems were highly deterministic. We had to really think, what are the foreseeable operating conditions? Document that, review it independently, then implement. Think of those sequences. How does Agile fit in? It does. They're rigorously verified for each decision. Each decision the engineer makes, the designer, the implementer, and they map those, trace them to each requirement. So if you've been to some of our AFuzion training in the past, you've seen this optimal green snake. It's green because that's the color of American money. It's expensive if we deviate. We start with safety assessments, quality assurance. We build system level black box requirements. Then we follow standards such as DO-178, 278, 200, 254, 297. We create plans, standards, checklists, and we trace safety to systems down to hardware, software. We capture everything in configuration management, CM, and we have our first stage of involvement. It's like reviewing the building plans. Then we go to implementation, high level, low level, detailed design, code. We verify everything, validate, conformity review for all changes, and then we certify. This is the old world process. Well, things are changing. You've all used AI. Curious, have you used AI to code? Ooh, 2 years ago, it's weak. Today, wow, improving every week. The traditional world, the old world, we did things manually. It worked. Every aircraft you're flying in had mostly manual built requirements, some automated code generation, but most things were done manually. But today, let's be honest, we're doing pair programming. AI is assisting us. AI is designing, writing the code, and even in some cases, the test. Well, we need that independence, but we want to recognize the potential greater efficiency and maybe accuracy of AI-assisted world. So we have to think about security, not just defects, but the bad folks, the black hats, the hackers. Well, in the real world, we need to assess safety, continuously develop the system, software, hardware, but to think of security, the yin, the yang, the complementary. We assess security. We say, what are the weaknesses of my development environment, my implementation? Where are the weaknesses in my architecture? What are the threat vectors? How could I be hacked? How could I detect, prevent, relegate, mitigate? And then I develop following that security system. Well, I need continuous feedback because designing complex systems is an evolution. And this is where Perforce comes in. In just a couple minutes, they'll explain how they fit in because we don't know all the answers at the beginning. Think of yourself, your life. Did you know all the answers at the beginning? Well, at the beginning, you were rather small, kind of like your brain. You evolved, you're still evolving, and that's what our complex systems are because you folks, each of you, is a complex system. Now, after we complete the feedback, we recognize that there's 14, this is for aviation, DO-326, 14 security architecture principles. We don't have time to go in depth in this, but if you want more information, there's another video. Just search AFuzion Cybersecurity, you'll find it. Or look at our white paper on the afuzion.com website. We start with defense in depth. We think of the integrity of connected equipment. If equipment's not connected, security is much easier. We want to promote continued secure operation. That's the aircraft, airworthiness, or the system, the ground system, the satellite, the medical device, your car. Your car is a complex system with over 100 million lines of code in today's modern car. You want to prevent bypass of security barriers. Keep it simple, detect, restore. That's at the platform level. And then in red, at the multi-system level, we want to refine the attack paths, understand them. Consider very specific security processes. Minimize the external interfaces because they're all potential threat vectors. Disable any unused interfaces and prove you did. Promote independence, isolation. At the item, and remember, we have aircraft, system, subsystem, equipment, items. Items can be complex. Hardware and software is complex. It has logic. You cannot fully test logic. So at the item level, we need a process. We want to ensure error handling, least privilege, control access. These are our principles that we work with. So now, folks, your world, today's world, for AI, we have to think, which language model should be used? Can I get by with a small language model, or do I really need a large? How am I going to verify it? Is it truly deterministic? Oh, it's a model. It is not. It's not. So how do you prove what's inside? Because what's inside is the stuff, the item, you can't see. But it was developed by humans. Which humans are perfect? None. Which AI is perfect? None. For security, we have to think, what are those threat vectors? Have I considered all of them? What are their vulnerabilities potentially and in reality? And then, let's be honest. Life is continually changing, throwing us new surprises. Security threats continuously evolve. We have to prove, guilty until proven innocent, that we're keeping up. So we need some answers for this, folks. Yeah, we need some answers, and that's where Perforce comes in. So right now, Steve Howard from Perforce is going to dive in, starting with the impact of AI on software safety and security regulation. Okay, so it's a pleasure to introduce Mr. Steve Howard, and at the end, his colleague Courtney Hendrickson is going to be covering Q&A for us. So I see we're getting some questions coming in. Thank you very much. That means you're engaged. I'll see you back in a few minutes after Steve. Steve, Courtney, go ahead.
Brilliant. Thank you, Vance. That's very kind. Okay, so as Vance introduced there, really the focus of this topic is to look at how AI is really starting to impact both our software safety and security regulation. And it's interesting because standards are developing, not necessarily just in the aviation space, but outside of that as well. In fact, you know, all over, it's starting to become a concern, and people are scrambling a little bit to see what it is that can be done to try and mitigate those risks and reduce those risks, as Vance said. So there are several examples here of new standards that have come to light over the last year or so, including very, very high level standards like the EU Artificial Intelligence Act, but also slightly more granular extensions to other standards that already existed. We'll have a look at each of those in turn and just see what they mean. And of course, these are from a broad spectrum of industries, across industries, and also across kinds of standards, if you will. So starting with the most high level, perhaps, in terms of its overall focus, but the idea, the EU itself as a whole, European Union, has come up with this basic structure to various articles around AI systems and what it means for them to be usable, safe, secure. Article 15 deals with accuracy, robustness, and cybersecurity specifically. And it addresses the concept of these problems from high-risk AI systems, where we're talking about components or management systems that within the operation of critical digital infrastructure. And that's outlined by the EU as things like road traffic management or water supply for civilians in the community, gas, heating, and electricity, and so on. Those are the critical systems that we need to make sure are safe and secure, robust and accurate, of course, with AI considered as part of them, around them, interacting with them, and so on. So it is a very, very high level document that kind of starts to define what the problems are and how we might consider dealing with those issues. Further down the food chain, if you will, eventually we get to things like functional safety, where we're actually defining the impacts of, in this case, AI on functional safety systems for general electrical and electronic systems. Essentially, the TR 5469 is an extension of, or evaluation of, the 61508 standard for functional safety in electric and electronic systems, but how that applies then for AI algorithms, where they're used within it, and also where AI is used potentially within the work around the safety case or the tooling that's used to develop it in those systems. And in many cases, they are addressing the problems and the ways that we can deal with this in terms of a SOTIF approach. And SOTIF is the safety of the intended functionality. We can't test everything. We don't know how everything's going to behave because of non-determinism, as Vance mentioned. It's not always possible. And so we have to try and use this concept of safety of the intended functionality as a whole and work out what could happen potentially and make sure that we've done enough to mitigate that. In the initial TR 5469 release, the idea is that we're classifying AI according to its usage levels, whether it's used in the field, actually in the device, use in the development of the system, and also there's levels for C and D. These levels, you know, where they are sitting. C and D is then where it's not used directly in the safety path of any kind. So there's kind of these different levels of classification, and obviously where it's actually used in the field would be considered the highest risk, and that's the one where most of the mitigation would be, you know, very much required as mandatory. So this is what it's doing to try and address this, and these standards are starting to evolve. This is just one example of functional safety that's starting to creep into AI usage in these systems. There's also on the other side of the pond now, moving across from Europe, we've got the NIST standards, which are, you know, many standards out there around the NIST SP 800s, all to do with software security and so on, and use of secure practices in development of software. Well, the NIST SP 821 8A is actually a specific standard around the use of secure software development practices for generative AI and dual use foundation models. So this is specifically dealing again with security of AI, and it's a new addition to that sequence of standards from NIST. And in this case, the goal is very much to identify the practices and tasks that are needed to address these new risks that are being introduced by the use of AI models. And finally, I wanted to introduce another standard, in this case, a coding standard related to generative AI applications. And this one's the OWASP, or Open Worldwide Application Security Project. It's moved from web application to worldwide. But this is a non-profit foundation that really provides guidance and resources for community-driven standards around building and maintaining secure software. And it's a very high-level standard, again, of the kinds of issues, in this case, just the top 10 issues that are most likely to cause security vulnerabilities for these applications. So again, originally it was for sort of web and web technologies and so on, but it's more general these days. And in this case, they were actually building this list of top 10 risks and mitigations for the use of models for software and for the use of LLMs and generative AI applications. So it's an extension of the existing OWASP top 10 general security guidelines, if you will. So these are the kind of movements we're seeing within the market in order to address the problems that AI might bring for safety and for security. But bear in mind, we have still got existing standards that we may need to be aware of and to deal with our AI system. So obviously we've got the functional security standards that have already been in existence, such as the DO-326/ED 202 series documentations from both the US and the European aviation authorities. And we have examples to closely linked standards there as well, like the IEC 62443 for automotive. Vance mentioned automotive. Again, the security risk within large automotive systems and many modern vehicles that have so much connectivity and application usability from outside the vehicle if you've got a communication interface. So all of those things kind of build up the idea of functional security. In the case of the DO-326 standard, of course, we have the airworthiness security processes at AWSP, and there are 7 of those generally around this whole idea of bringing security considerations in from the very start and planning what's going to make sure we mitigate those risks, and also where those risks lie by assessing the security risks up front and thinking about where those attack vectors may be. And that's how they're all based, you know, basing the idea on we assess what the problems could be, and then we try to find ways to mitigate those risks thereon. But it's generally that all of these standards have roughly the same principles, and it's about how we can potentially extend those to using or to working in systems that include AI, or certainly use AI in their development. So with all that in mind, we'll now have a quick look at what the benefits and limitations are of using AI in software development, but specifically with this concept of secure and safe software development as the backdrop, as we have in our aviation and defense systems and so on. First of all, AI is becoming fairly mainstream in its use within software development itself. So in a survey done last year by Stack Overflow of developers in their AI section for that developer survey, 84% of developers that replied on that survey said that they use or plan to use AI tools in their software development. And 51% of professional developers within that survey were already using AI daily in their development work. So it's already more than 50% of people using it, and the expectation is in the near future will be very close to sort of 85% of all of those developers working with AI in the actual process of software development. So it's mainstream. And the interesting thing about using AI for software development, and it is very good, as Vance said, 2 years ago, this was fairly difficult to use. It wasn't practically possible to use it for real world coding. But it is happening now. It is working and it is being used. And those AI models have learned what they know about writing software from real world code. Often a lot of the open source code out there and so on, or anything that's been checked into GitHub maybe. And the problem is that this real world code includes insecure patterns. It has security issues, especially if it's used out of context. There might be new security issues caused by the use of known patterns being used in unknown contexts. And that means that we lose a little bit of trust. And that's already a healthy amount of distrust, I guess, of AI that's built into developers. I think we're all naturally slightly skeptical that a device of any kind can generate, code that's better than we can, I suppose, as a development community. So developers automatically have maybe a built-in distrust, and that's healthy. But in the Stack Overflow survey from last year, in fact, it was determined that only 3% roughly highly trust, as they marked. Obviously, they graded the trust levels, according to what people thought, and only 3% actually said they highly trusted AI-generated code. And that's probably sensible because of those issues that we know about. So if AI is writing more code, and we know this is now becoming a mainstream use of AI, code volume and velocity are definitely accelerating. We see that in our own development here at Perforce, that we're getting more code. Development teams are working quicker. This is great. This is what tools are intended to do for humans. We use them to improve our performance, and it's definitely working. But our safety and security practices, they need to keep up with this. They need to scale with AI. And that may involve using AI, of course, but there are also problems with using AI because of that non-determinism in our functional safety and security requirements. So how can we harness AI, perhaps, to help us improve the performance of our safety and security practices such that we can keep up with the new development practices that we're starting to see in the world of AI? And really, that's where we come in from Perforce and the power of static analysis to help us here try and resolve some of these problems and mitigate some of these risks. So just as a quick introduction, static analysis is a well-known principle. It's been around since the late 1970s as a concept, and obviously those static analysis tools have evolved a great deal over the years since the late 70s, and now do a very good job of deterministic verification of code quality and security issues. They can be used to enforce security standards and make sure that code is compliant to those known standards, and standards that have developed over many years from lots of experience of lots and lots of programmers and the issues that can arise. So those standards have a wealth of valuable data that we can actually use to check against new code that's being written. And the good news about static analysis, because it's running deterministically and it will run against those known standards and apply to all code the same set of standards, then it's going to not judge or anything between differences in human and AI written code, but treat them all similarly and with the same requirement. And of course, static analysis is very scalable. So it helps that we can keep up with the speed of AI through automation in CI/CD, for example. We can ensure that all of that code that's being written is also being checked. Now, going back to the coding guidelines, and obviously there are developments in coding guidelines, as we saw with the new OWASP top 10 for LLMs, actually to deal specifically with AI code and code around AI systems. But there are already lots and lots of widely used secure coding guidelines, such as OWASP, but also DISA, STIGs, CWE, and CERT. And where they have been built to capture many person-hours of expertise and experience into a single convenient set of rules, and those rules that can be enforced with our static analysis. So they're very valuable sources of data, of knowledge and experience. The great thing about static analysis, as I say, is we can integrate it very conveniently into our CI/CD processes, for example, so that we know we're checking those requirements for the coding standards or whatever with each step of that process. And I take a process here that's grabbed from the GitLab view of the world, if you will, where we have a central master branch, which is where we will eventually release from. And on that branch, we have branches coming off it for the different features that we're developing. So from the master, we branch out to a feature branch. The developer then works locally on their desktop, maybe with their IDE, writing new code changes, adding code, changing code that's already in existence. And at that point, we can use static analysis to perform scans as we develop. So it's very, very efficient. It's finding issues as soon as they're introduced. Once we finish with that stage, we commit our changes, the CI pipeline tends to run. And within the CI pipeline, again, it's very easy and very convenient and very fast to use static analysis to perform a delta analysis scan of the changes on that particular feature branch relative to the master. And then we typically have some kind of review process where the results of those scans, together with all sorts of other checks that would be performed on the CI pipeline, centrally in a controlled environment, we can reproduce. And those reviews would then come up with an overall decision of, do we want to go back and make further changes, or are we happy that this is now ready for merging? Once the change is accepted, we merge back into master, and that's when we would then perform our next full build of the software to make sure it still compiles, of course, normal CI/CD, but we can also perform a full scan from the analysis side to be able to generate our compliance documentation, safety, case information, whatever it is that we need at the output of our static analysis and those checks against the rules to be. So that's where we see static analysis fitting in. And really, this is wonderful because we can detect issues and we can make sure that we are always checking that we're meeting the required standards. But maybe detection alone is not enough, because now we have to go and fix issues that we're introducing. Or maybe we're not introducing, but AI is introducing. And it's introducing that new code at a new scale, much faster than we used to have with manual development. So perhaps manual remediation, which is time consuming, is not the ultimate answer that we want when AI is helping us to write the code in the first place. So what if we had a way to automate fixes? We know that we're going to introduce new issues because AI is writing code, and is writing code based on learning code development, which includes potential mistakes. We're using static analysis to detect those mistakes as an automated process very efficiently as part of our CI pipelines. But how can we make sure that once we've done all of that, we deal with the problems very, very quickly? And this is where we can use AI again, taking the analysis data from our static analysis, rich, deep into procedural analysis, and using that information to propose fixes to the problems that we originally created with the AI. So this is something that's a new feature within our products of static analysis, but something that really allows us to then scale to deal with this challenge that AI is bringing to our software development life cycles. And whenever we do this, we automatically reanalyze the code as soon as there's a proposed fix to make sure that it's fixed the problem. So we're checking it again against the original standard. And there must be a developer in the loop approval to make sure that they are happy with the change proposed. So we've always got that developer approval and review process in a nice granular step within that overall development lifecycle. So it really transforms the static analysis just from a reactive tool here into a kind of a collaborative coding assistant for the developer to use to make sure that everything they're doing is being checked for new potential issues and that they're aware of what's then coming out of it and can use the AI again to help them fix it. And at this point, I would like to just show a quick demonstration of this working in real life. So I'm going to just quickly switch here to a different screen. Bear with me. And hopefully you can now see a new screen with my, I say confidently, with my loaded application. Okay, just bear with me. Right, brilliant. Okay, so I'm going to go to Visual Studio Code. And within Visual Studio Code, I've loaded a project here. So this is the OpenSSL project, open source download that I've taken from the project website. And this is a relatively recent version, but obviously OpenSSL is used in many, many applications across all sorts of industries and operational tasks. And it's obviously very clearly in a security context, which we want to make sure we have the best possible results in. So I'm going to open up a single file from this at the moment in my Visual Studio Code. So obviously I've loaded this in here. I've installed the Perforce Clockwork Analysis plugin in this case. And obviously we've also got the GitHub Copilot chat on the right-hand side here built into Visual Studio Code. And for that, I've just at the moment used a free account. So I don't get many choices in my models anymore. That's changed. It's selecting the auto model. And this is the free account. So obviously in most cases, our customers would have their own local LLMs or certainly private LLM arrangements with various LLM providers. And as a result of opening up that file, it's updated my analysis here and filled in, details of what we have in the code according to a certain standard. And in this case, I am just using the CWE standard for general C and C++ issues to apply to my OpenSSL project. Now, as I change my code, as I'm coding, in this case, I've just introduced an unused variable, the analysis will occur in the background. So as I make my changes, you'll see that it will pop up in the background, say I'm doing some analysis, and then it will update my analysis results in due course with any changes. Now, this is quite a big project. There's about 500,000 lines of code in total. But the beauty is the analysis is working incrementally. So it's not having to analyze everything, it's analyzing the changes. And as a result of that, we very quickly get our outcome, which is that by making that change, we've introduced a new issue. So that's what we're seeing in there inside the IDE as a developer. Now, with these, you'll see that there's also CWE references. In the case of these critical issues at the top here, which were already existing in the code before I made the change, you can see that they have a CWE 476 and 690 reference. And with any of those, the beauty is that we can actually just show the help for that particular rule. It just connects up to our local help server. And from there, it will tell us about that particular type of issue. In this case, it's a null pointer dereference issue. And there's some text on, what kind of vulnerability and risk this presents, what an example looks like and how to fix it, other checkers that might be in a similar vein, and also external guidance for those various issues. So in this case, we said it was a CWE 476 or CWE 690. And if you click on the help for those, it takes you through to, in this case, the common weakness enumeration, specifically the Article 4, CWE 476, and explains, again in their language, what it is from this coding guideline that they recommend as the problem and the risk and the issue with that. As a developer, I'll go back to seeing my problem, and as I say, you can click on this and see where exactly it is in the code that the issue is found. What's happening in terms of this little trace back here is it's telling us through, as if we'd had a crash in our code, and the debugger would provide a sort of a trace of the stack, stack trace of where you've been, and all of the different steps to end up with your crash. The static analysis is kind of doing the same thing in reverse. It's predicting if you go down this path, where you go down this path, this is the result you would have, and this is where the null pointer dereference would happen. So in other words, here we're assigning the result of the X509 name entry get data function to the data pointer, and then if we click through, we can actually see where that null return comes from within the function. So this is where the X509 name entry get data can return a null value, and of course then finally where that is explicitly dereferenced without being previously checked to see if it could be null. So this is where it's an unprotected dereference. That's where the problem can occur. So the beauty is, once we have installed the plugin, we have the option to now fix these issues using the Klocwork analysis data in this case, or the QAC analysis data if we're using the QAC engine underneath. And simply what this is doing is passing that data to the LLM via the Copilot chat plugin. And it's passing very, very specific data. It's passing the deep interprocedural data around where this particular issue manifests itself, how we got there, also the relevant help pages and information that we saw from the local help documentation, and also other guidelines like CWE or CERT or OWASP or whatever it is that we're working to. Once it has all of that data, the LLM is much more likely to come up with a more accurate fix for that particular issue. And you can see here it's now starting to make changes to the code. And of course, this can, I don't know what this will be. Quite often it's this result that it comes up with. And you can see now it is proposing a fix, which includes checking the data pointer for null. And in the event that it is null, then it returns -1 from the function, which is a similar behavior to the line above here, where if there is an index of less than 0 passed in, or whatever it is that we pull from a function above, then it returns -1. So the AI is kind of determined from reading the code around the particular problem that in this case, the -1 probably represents an error condition from the function. And so it's matched that when the pointer is null as well. So it's quite clever in how it's proposed this fix. And obviously it explains on the right-hand side how it came about, this particular decision, and so on and so forth. Now, the really nice thing, as I said before, is that once we have this proposed fix, the analysis will happen in the background. So it's working now on the updated analysis based on this proposed fix. And then finally, the developer has the choice as to whether they keep that change or undo that change based on what they think from understanding the problem. And it's up to the developer finally to have that last approval, which is very important if we're dealing with functional safety or even functional security, to make sure we're not breaking something else. So that's really what we're trying to achieve here. And obviously, as I say, the important thing is that once we've made these changes, we have the updated analysis, but also we have the opportunity here now to interact with this in the chat prompt as well, and say, okay, perhaps add a little comment to explain the fix, what it was that you were trying to achieve with this fix, and why you did it, just so that when we come to review this within that CI pipeline downstream, the reviewer will have the information as to why that code changed and what it was trying to achieve with that code change. So that's really what we're trying to see there. And you can see now it's just finally listing those change results based on the fix proposed by the AI. And that will hopefully see that issue disappear. And also, I think it will also impact the following issue because they were both related to a null pointer dereference of the data pointer. And you'll see that then pop up just with the one remaining issue, which was the one I introduced in addition to do with the local variable. And there we go. So we now have just the one local variable issue left, and everything else has been resolved. We can keep that, and off we go. So that's how the system is intended to work for the developer to make maximum efficiency. I'll just go back to our presentation to finish off, and then we'll hand it over to Courtney for some questions. So that's really what we wanted to show here today. Okay, so very quickly.
I'm really enjoying. Well, I was just saying, very impressive. I'm really enjoying. Yeah, I learned a lot too, Steve. Pardon me for interrupting. That was fantastic.
Thanks, Vance. Yeah, so really just to summarize, and then we'll wrap up and hand over to Courtney. Really, the benefit of this is that we're using AI's performance to do the things that AI is good at, which is adding the intelligence to our process, but it's based on rich contextual static analysis data that it's allowed to come up with those fixes. It proposes remediation. We then confirm that the remediation has solved the problem, and the developer can approve the final sign off of that change. And so really, in summary, AI is changing the calculation for us for code quality and security. And we must be able to make those processes around the development scale at the same speed. So AI increases our code volume, increases our complexity, and even our rare defects that we see, you know, if we're finding even a few defects per 100,000 lines of code in AI generated code, it's still a problem when we're dealing with the scale that we're going to have AI writing code. And so our manual code reviews cannot keep up with that. And that's why we need to find alternative solutions. At that point, I shall graciously hand over to Courtney, who's going to just bring up any questions that we've had during the webinar. Courtney, over to you.
Thank you, Steve. Before we do answer some questions from the audience, and there are several here, I would like to take a second to note that the QR codes on the screen here can be accessed to learn more about Aviation and Perforce software solutions. So please check those out. With that said, again, some great questions here from the audience today. With the first question being, do the Perforce static analysis tools support the DISA and OWASP standards as well as CWE?
Yes. The demonstration there was specifically with the CWE rule set applied, but it works the same way when you use either the CERT, many different versions of CERT for different languages, of course, and also similarly OWASP standards in the same way.
Great. Our organization develops code entirely on air-gapped networks. Will these tools, including AI remediation, still work?
Oh, that's a really good point. Yes. So indeed, of course, when you're in very secure environments, air-gapped networks become quite a norm. And in those cases, we won't have any communication to the internet or the outside world. So certainly it will work. You do have to have a local LLM, of course, running within the network that you have within that air-gapped network. But it will work with that local LLM then. And everything you saw in the demonstration would work the same way, except we could not link out to the CWE documentation because that is on the internet at large. And unless there's a local cache of that, you wouldn't be able to see that. But everything else that you saw would work the same way. Yes.
Great. All right, next question. Do Klocwork and QAC have DO-326A qualification materials?
Yes, so it's DO-330, specifically the qualification standard for DO-178C, and they both have that. So yes, that's something we can provide. They have the full qualification test kit and also all of the various documents you need for that. Yes.
Great. All right, moving on. Today and tomorrow, what is the aviation roadmap for incorporating AI into avionics development and flight deck?
Or maybe that's one for Vance.
Yeah.
I'm glad I had some coffee for that one. It's interesting. We used to call EASA the FAA's little brother. As a father of multiple boys, little brother wants to become big brother, and yeah, okay. Today, EASA is bigger and in some ways ahead of FAA. And in this case, they are. So EASA's got a good roadmap. We'll see if FAA follows. We don't like divergence. In aviation, standardization, we want convergence, okay? Harmony, right? Equalization. So EASA is moving forward with AI, especially for level C, level D, okay, on Part 25 aircraft. That's the large stuff you fly in, passenger aircraft. FAA is not yet, okay? So we have some trepidation when we work with EASA, and we work all over the world at AFuzion. We recognize that the DAL, development assurance level C and D, there's not a lot of action at level C and D. Most of the flight deck avionics are level A and level B, okay? But for level C and D, we do have a roadmap for AI, and it's really cool. The key is that there must be a human in the loop. We can't solely rely on AI to design, code, and test. We need that human, okay? And we've all seen AI code 2 years ago. It's pretty lousy. Today, it's pretty good and getting better. So it's coming in about 3 or 4 years to Europe, probably 5 or 6 years to USA. Remember, I'm old enough to remember we could not use calculators in school. Unfair advantage. Are they accurate? Well, today, everyone's using AI. In fact, this isn't really me. This is an AI generated me. Maybe.
Who knows? All right, just looking at the time here, it looks like maybe we have time for one more question. If I'm using AI to develop safety critical, what things should I be aware of to certify my system later to any safety critical standard? Let's take that.
That's futures. That's got to be you, Vance.
Okay, then I need another sip of coffee. Got to have proof. In all your countries, if you're in a good country, and probably you are if you're allowed to use the internet and watch this, you are innocent until proven guilty. Good legal supposition. Well, not in aviation, not medical, not automotive. You're guilty until proven innocent. So that's the key. Prove your innocence. You prove that by having detailed written requirements with review, standardization, always a human in the loop. You have design, yeah, we use AI, but it's reviewed, augmented with verification proof of human in the loop. Yeah, we code with AI, let's be honest, we do, but we have that human augment review, same with the testing, okay? So the human's always in the loop, yeah.
Great. All right. I think that's all we have time for today, right? But as Vance did mention earlier, if we didn't get to your question, we will reach out to you via email to make sure that all of the questions asked today are answered. I would like to take a second to thank our audience for your attendance and participation today. And of course, thank you to our presenters, Vance and Steve. We'll see you next time, everyone.
Thanks, Courtney. Thanks, Steve.
Thank you.
Bye now.
Bye-bye.
Bye-bye.